Hi, everybody. I'm coming back with just one video for you, one example, basically, to show you sort of the common strategies for doing proofs involving the greatest common divisor. So just as a brief reminder, the greatest common divisor of two integers a and b, if you have two integers, then the GCD of those two integers, the greatest common divisor of a and b, is the largest integer that you can find that divides a and also divides b. So there's sort of these two aspects of this definition. One is that when you are showing that something is a greatest common divisor of two numbers, you have to show first that it does divide both of them. So that x is a common divisor, that is, it divides a and it divides b. And then the second thing you have to show is that if you take any other common divisor, if you take a number y, such that y divides a and y divides b, then you have to show that x is at least as big as it, is bigger than or equal to it. You know, that says that x is the greatest of the common divisors. So proving that something is a GCD, it sort of involves these two steps. Okay, let's see how this works in practice. The proposition says, if a and b are integers, then the GCD of a and b, the biggest number that goes into both a and b, should be equal to the GCD of a plus b and b. That is to say, adding b onto a doesn't change the value of the GCD. Okay, so let's go ahead and see. Here's the proof. We're going to do this, and we'll do it. This is an if-then statement. It's a conditional statement, and we'll do this with a direct proof. This proposition, the way I think of it is, it's interesting because if you have two integers and you find the biggest thing that divides them, then you can add a copy of one of the integers to the other, and then those two new integers that you have, they still have the same number that divides them. Adding that thing on doesn't somehow give you more divisors, which is kind of interesting. Okay, so what's the proof? Let's do this direct. Suppose that a and b are integers. And what I'm going to do is we want to show that these two things are equal. So I'm going to go ahead and give this one a name. So let D equal the GCD of A and B. And then what do we know about it then? Well, 1, D divides A, and D divides B. And also, so this part is just from the definition of GCD. This says that D is a common divisor. And then the next part will say that it's the greatest. And for any, let's call it x, such that x divides A and x divides B, we have that x is less than or equal to D. So this says if you take any other common divisor, it will be less than D. So we started with our two numbers, and we're taking the GCD of those two numbers. We're calling that D. And now what we would like to do is consider what happens when we divide that into a plus b and b. We're now looking at the two numbers a plus b and b. So I'm going to break this up into separate claims because it's easier to think about that way. You don't have to do this. It's just sort of useful. There's different things we need to claim. So here's the way that I'm going to do it. This number D that I've found, the GCD of this side, I'm going to show, first of all, that D is a common divisor of these two numbers. And then I'm going to show that it's bigger or equal to any other common divisor of those two numbers. So claim is, I claim that D divides A plus B and D divides B. That's like saying it's a common divisor of these two numbers. Proof. So this is like a little mini proof. Well, how do I know D divides A plus B? Well, I know D divides A and D divides B. Since D divides A, we have that A is equal to dm And since d divides b, I have that b is equal to dn for some m and n in the integers. Then, let me see. To establish that d divides a plus b, let's just look at a plus b. A plus b is equal to dm plus dn by substitution. And factoring out a d, we get d times m plus n. That's what a plus b is equal to. So this says that a plus b is equal to d times this number, m plus n. I can note that m plus n is an integer by the closure of the integers under addition. Because we knew that both m and n were integers already. That came from our definition of divides. And so when we add them together, we get an integer. Okay, and thus, since a plus b is equal to d times an integer, this means that d divides a plus b. So d divides a plus b by the definition of divides. Okay. In this claim, I claimed that d divided a plus b and d divided b. So d divides a plus b, that one I've finished. I've shown d divides a plus b. I now, in order to finish this mini claim, I'm going to prove that d divides b. So next, how do I know that d divides b? Well, that was given to us. D was the GCD of a and b, so by definition, d divides a and d divides b. So I could just add here. I don't even need to prove anything for this one. It's just something we know already. It's given to us up here. So, also notice d divides b, and that was by definition of GCD. That number d came from the GCD of a and b, and by definition d therefore divides both of those. Okay, so this claim is now proved. So I can put a little box at the end of this claim. My next claim is the following. It says, well, we need to show, what am I doing here? I'm really trying to show that this number d, which was the GCD of a and b, I'm trying to show that that number d is also the GCD of these two. And what I've shown so far is that d is a common divisor of these two. And now I just have to show that it is the greatest common divisor. Claim d is the greatest common divisor of a plus b and b. So this is somehow the second claim. We've shown that d is a common divisor of a plus b and b, and now we show d is the greatest common divisor. And then we will have shown in our theorem that d, which was the GCD here, is equal to the GCD of this. That's the strategy. Okay. So how do we prove this claim? Proof. Suppose, let's call it E is a common divisor of a plus b and b. And then I'll put this in a different color to show it's not really part of the proof. What do we want? We want to show that if E is any common divisor, we want to show that D is bigger than or equal to it. So that's somehow our goal that we're aiming for in this. So we've said to show that D is the greatest common divisor, we say, suppose we take any other common divisor, E, can we show that D is bigger than or equal to it? Okay. So how do we do that? Well, E is a common divisor, so that tells us that E divides A plus B, and E divides B. That's just by the definition of being a common divisor. That's what being a common divisor means. So, A plus B is equal to EM, and B is equal to EN for some M and N in the integers, and that's by the definition of divides. Okay. So, the question, I guess, is how do we do it? We're aiming for that D is bigger than or equal to E, and we have these facts about E with us. So let's do the following. Let's follow our noses. We know that A plus B is EM and B equals EN. I'm just going to go ahead and substitute this one in here. So this says that A plus EN is equal to EM by substitution. And then let's just move the EN over. Let's see, A is equal to EM minus EN. So A is equal to E times M minus N. And this is just sort of following my nose. We now have that A is equal to E times something. I'm just going to show that this is an integer, and therefore E divides A. Let's do that. So note M minus N is in Z by closure of Z under subtraction. So E divides A by definition of divides. Now, I just want to point out E divides A. We already knew that E divides B. So since E divides A and E divides B, the reason for those is just they're above. The fact that E divides A is right here, and the fact that E divides B was given to us. Since E divides A and E divides B, E is a common factor of A and B. All right? What we're doing now is we're managing to take this E, which is a common divisor of A plus B and B, and we've now related it back to just A and B. And the reason that this is helpful to us is that E is a common factor of A and B, and we're trying to show that D is bigger than E. Well, D is the greatest common factor, so in particular, it's bigger than any other common factor, which means, thus, E is less than or equal to the GCD of A and B, because that's just the definition of the GCD, is it's greater or equal to any common factor, and that GCD is equal to D. So E is less than or equal to D. Okay, thus, what have we shown? We have shown that this number D is bigger than or equal to any common factor of A and B. So D is the greatest common divisor of A plus B and B. That's what we have shown. Thus, D is the GCD of A plus B and B. And that completes both the proof of this claim and also the proof of the entire theorem, since the theorem was proving that the GCD of this guy was equal to the GCD of this guy. Okay? That's the end of the proof. You can see that somehow reasoning about the GCD involves kind of going back and forth using these two properties. One, that it's a divisor of both, and then two, that it's the greatest of all the divisors. And sometimes it requires a little creativity to see how to work that into a proof. And that's what you'll be practicing in the current assignment. Best of luck to you.